Assalamualaikum and good afternoon everyone. My name is Muhammad Ashraf bin Ebihan. I am the group leader of Group 2 in our subject Aircraft Design 2 Skma 4523, which our lecturer is Dr. Wan Zaidi and also Dr. Muhammad Nazri. So I would like to present the preliminary and also the conceptual design of our aircraft. And first of all, let's start with the objective. So our objective is to design a real working aircraft. To generate the detailed structural design of the main component of the aircraft, we also need to analyze the loads acting on the structural part. We also need to design an aircraft system components such as the control system, the avionics, and also the power control system. We also need to prepare the assembly drawing of the aircraft airframe, integrating all the structural components. We need to demonstrate the ability to think critically and also to solve problems regarding the aircraft design. We also need to adopt the ability to work together in a team and also to produce an aircraft design. And finally, we need to demonstrate the ability to present our ideas and also our solutions to a specific problem. So let's start with the design selection. For our wing configuration, we are using a rectangular wing, which is the factors in choosing this rectangular wing is because this is the most wing configuration among the aircraft. It also simplest wing to manufacture. Since it is non-tapered, it also suitable for the light aircraft. It is easy to design and also easy to maintain and to carry more fuel for a real working aircraft that are using fuel to fly. And the next one is the fuselage configuration. We are using a monocoque structure, which includes the skin, former, and also the bulkhead. It relies largely on the strength of the skin to carry primary loads. So in this case, skin of our aircraft design are very important since it is responsible to carry a primary loads, and we are using the EPP foam, so it is very suitable and it is very strong to carry the loads of our aircraft. It uses the former bulkhead and frame to give shape to the fuselage. It also the heaviest are located at intervals to carry concentrated load, and also the design is simple and also easy to fabricate. For our tail configuration, we are using the conventional configuration, which is because of it is most common form in the aircraft. It also provides the adequate stability and also control with lower structural weight. It is also low risk and easy to control, easy to manufacture, and it is most efficient for speed RC plane. Since we are designing an RC plane, so this type of tail configuration are the most suitable configuration for our aircraft. And for landing gear configuration, we are using the tricycle configuration. It is also most common form among the aircraft. It can also prevent the nosing over when the aircraft brakes, enable a higher landing speed. This is because most of the RC plane are having trouble during their landing on the ground. This is because when they are trying to land during a higher speed, they will experience a nosing over, which will end up breaking the propeller. So we don't want that kind of problem in our aircraft design. So we are using the tricycle configuration. It can also provide a better visibility during landing and also maneuvering. It can also prevent the ground looping of the aircraft, and it is also most efficient configuration for speed RC plane. And this is the schematic of electronics diagram. We are using the TCB3S2200 mAh LiPo battery, which we will transfer to a Skywalker 30 ampere ESC. For motor, we are using a Turnigy D28376/8, which are having a 1100 kilovolt, and then transfer to a FSIX 6-channel 2.4 GHz receiver, and then we are using a FlySky FSIA RC controller, and we are using 4 Tower Pro 9G servos. And for the material for our aircraft design, we are using the EPP foam, and also we are using some of the plywood to act as the inner structure of our aircraft. So EPP foam are very suitable foam for our aircraft since it is very light, but it is very flexible and strong to overcome the loads acting on our aircraft. So we move to the weight and cost estimation of our aircraft design. So as you can see, there are some of the parts that have slightly higher weight compared to the others, which for example our motor energy, which is 100 gram, and our lipo battery, which is 200 gram, and plywood also 300 gram, and the most important part is our payload, which we are using plasticine, which is 500 gram, and the total estimated weight of our aircraft is around 1.467 kilogram, which is still acceptable and still below the limitation of our aircraft design. And for our cost estimation, as you can see, there are some parts which are quite pricey and quite expensive, but we still need to buy them. For example, our motor energy, which is cost around 120 ringgit. Our receiver, fly sky receiver, which is around 66 ringgit, and our battery, which is around 59 ringgit. And the total estimated cost of our aircraft is around 382 ringgit and 86 cents. So that's the rough estimated cost in designing our aircraft RC plane. Right, so we move to our aircraft specification. For our aircraft design, we are having a wingspan of 1.2 meter. Our mean aerodynamic chord about 0.17 meter, and our fuselage length is about 0.73 meter. For our wing, for our airfoil configuration, we are using NACA 2412 with an aspect ratio of 7.06. Our wing area is 0.204 meter squared, and since our wing is non-tapered straight high wing, our dihedral angle is 0 degree. And the final part is our overall aircraft drawing. So this is the rough drawing of our aircraft. We have the side view, we have the plan view, and we also have the front view, and it is include the dimension of our real scale aircraft, which will be used in the next part of the calculation, the next further calculation, and the next further analysis in our aircraft design. So that's all from me for the preliminary and also the conceptual design. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nasir Biyazi, and today I would like to start my presentation and discussion on the propulsion and performance. My group members are Ahmad Amirul Ami bin Abdul Wahab, Muhammad Azmi bin Bahjam, and Nurul Atifah binti Zulkifli. So first thing is the motor selection. Motor selection is very important because it will generate the thrust for an aircraft. So there are three types of the aircraft on the left of the table, and the thrust to weight ratio on the right of the table. So for the type of aircraft, we have glider or trailer, scale flight, sport and slow acrobatic, fast, and jets. For our project, we choose the scale flight because we scale down the actual aircraft into the RC plane. So based on the table, the suitable thrust to weight ratio that suits our aircraft is about 0.6 to 0.7. And then to calculate the thrust equals to weight time thrust to weight ratio. In this project, the weight should not be more than 5,000 grams. But we estimate that our aircraft will be around 1,500 grams. So to calculate the thrust, 1,500 grams times 0.6 thrust to weight ratio, and then we get 900 G of thrust during the takeoff. And then to choose kV of motor, there are few characteristics of kV to choose for motor. We have high thrust, medium thrust, low thrust, and lower thrust. Bear in mind that in this project, we are not focused on the highest speed, which is required lower thrust. So we choose the high thrust. The kV of motor that's suitable for high thrust is 1000 kV. And then how to choose the suitable power per thrust ratio with given value of kV. So this is experiment that has been done by Victor 2017. Previously, we calculate already. We knew that our kV of motor is 1000 kV. So from the experiment that have been done by Victor 2017, we get the power to thrust ratio is about 0.26. So from 0.26 power per thrust ratio, we can calculate the power required for motor by multiply power to thrust ratio multiply thrust. Previously, we already calculate the thrust, which is 900 G. Thus, the power required for motor is 234 watt. And then with this calculated value, the motor is chosen from manufacturer catalog. Higher value of motor, power with 40% to 50% more to fly easily at 50 to 60% of throttle. So currently we have two choice of motor, which is Teninji D2836 and Sunny Sky X2216. So we decide to choose Sunny Sky because it's have higher maximum power to produce for our aircraft, and it's very easy to get on the market compared to Teninji. So this is the detail of Sunny Sky X2216. The weight is 72 grams, and the maximum thrust about 1380 G. And then propulsion. Propulsion, it comes with from the motor catalog. So we have propeller AP69045, which required about 810 of thrust. So AP69045 is stand for the length of propeller is 9 inch, and the pitch is 4.5. So that's why the number is 9045. Okay, that's all from me. Thank you.
Assalamualaikum, my name is Muhammad Asmal, and I would like to present my part of the presentation, which is on the power required and the power available. So the general equation of power required is the thrust required multiplied by the velocity. But for an unaccelerated flight, the thrust required can be considered as the drag. So to calculate the power required, we have to consider the CD node and the CD induced, or in other words, the power required is the summation of zero lift power required and the lift induced power required. So for the power available, we have to first calculate the theoretical thrust, which is given by the power given by the our motor, multiplied by the diameter of the propeller in inch, and divided by the air density dependent coefficient, which is in our case we consider at 30 degrees Celsius at 1 atmospheric pressure, which we get around 0.0278. In the theoretical thrust, we get around 1300 gram force. As for the efficiency of the motor and the propeller, it's given by the thrust divided by the theoretical thrust. The thrust we got is from the catalog, which we calculate 70% of it, we got around 900, and divided by the theoretical thrust just now, so we got around 70%. Hence, the actual power available supplied by the motor is around 100.8 watt. And then we plot the power required, power available versus the velocity. As you can see at this intersection, this indicates the maximum velocity that our RC plane can go, which is around 27 or 28 meter per second, and at this area is the maximum excess power, which is around 58.56 at 14 meter per second here. And for the rate of climb, we plot the graph rate of climb versus velocity, and then we got the maximum excess power at the maximum rate of climb, which is around 2.9847. So for the endurance and range, since we use 4-cell battery, our endurance we got around 12 minutes, and for the range, by multiplying the endurance and the velocity, we got around 10,137 meters. So for the takeoff and landing performance, for the takeoff first, by using the following equation, we got around 10.58 meter, and as for the landing, we got around 17 meter distance. So that is all from me. Thank you.
Hi, I am Amirul Amin bin Abdul Wahab. I will continue our group presentations on propulsion. So I will explain to you about flight path. So from the graph here, it shows that our flight path of our RC plane. So based on our previous calculations on the performance, we estimate the flight path on our RC plane for the whole time. And the maximum for our RC plane, the maximum altitude is 20 meters at cruising speed. So the table here indicates our conditions during takeoff, cruising, and landing, and the time taken for the conditions and the altitude. So the highest altitude is 20 meters at cruising speed. So next, I will explain to you about flight current consumption, and thrust required. So there are also three conditions, which is takeoff, cruising, and landing. So we estimated the flight current and thrust consumption based on the percentage that we need. For example, for takeoff, we need about 70% from max thrust, while for cruising, we need about 50% from max thrust, and landing, we need less thrust, which is about 20% from max thrust. So since we required more thrust and current during takeoff, so the estimation of 70% from max thrust give us the value of 924, and the current required is 13.4 ampere. And the same goes to cruising and landing, but different in the percentage. So the next presentation is about the challenge that we face during design of our propulsions. So first one is during motor selections. It is become a challenge because we have to consider the characteristic of the motor in terms of voltage, torque, current, and velocity. The second challenge is performance estimations. In order to get a correct or approximate value of performance, we have to use appropriate value of weight, drag, density value, lift value that is correct to obtain the most correct and approximate performance analysis. For the performance analysis that explained before by Azmed, which is takeoff, landing, thrust required, and and others. So for the third challenge is unexpected event and condition that can occur during flying our RC planes. The example of the unexpected condition is bad weather, maybe heavy rains during our testing, and engine suddenly cut off. So we have to consider the glide angle when our engine is cut off. So this part will be explained by Afifa in the flight test. And the next example of unexpected condition is uneven runway that will make our airplane hard to take off. So I think that's all from me. Thank you.
A very good morning. So my name is Leong Jogi. So now I will continue on the presentation. So I will present on the avionics part. So first is the selection of electronics component. So basically the main consideration for the selection is the suitability and compatibility with the project. We need to ensure all components is should bear with each other and is best for the RC UAV that we design. Second is the price, where it is not so expensive but from a reliable brand. And next is the availability. We would prefer a local seller than an overseas one. So next, it's the first component is the transmitter. The component we select is a FlySky FSI6 transmitter. So the specification is as shown on the slide. So the reason we select this one is because it is a 6-channel transmitter. Second, it is a recommended brand for beginners. It is capable to up to maximum of 20 receivable memories. And next, it is also considered quite affordable price. So next is the receiver. So we choose a FlySky FSI6 receiver, and the specification is as shown on the slide. So this receiver is chosen because it is a same brand as the transmitter, and and it work well together and able to establish a good communication. So next, we will discuss on the transmitter and receiver communication signal. So the first is the frequency band. The frequency band chosen is 2.4 gigahertz, where it is able to do frequency hopping. So it is done by scanning the frequency band and find the best available channel during the transmission. So next is the antenna gain. So if you observe on the right side of the slide, so there is a high gain omnidirectional antenna pattern, where if you see the 3D pattern, where on the red color has the strongest radio wave, which is on the side, and on where the green color, which is on the top and bottom, has the weakest sign. So therefore the transmitter antenna orientation is recommended to be tilted on the horizontal, or even better, up and forward. So next is the receiver antenna orientation, where we recommend a 90-degree polarization. So the third is the communication protocol. So for the transmitter protocol, there is a AFHDS, which is automatic frequency hopping digital system, and AFHDS 2A stands for the second generation. So it is a digital protocol that ensures 2 or more radio can operate at the same time without interfering. So for the receiver protocol, we use a universal P. It has the universal PWM and PPM. Also the iBus. iBus is is the digital serial protocol developed by FlySky that allow up to 18 channels to be supported on a single wire. So next is the electronic speed controller, ESC. So a Skywalker 30 ampere ESC is chosen, where the specification is as shown. So the main consideration of selection is we need to ensure the ESC is able to support and work together and work well with the electronic motor, propeller and battery. Also, we need to ensure that it is able to it is able to support a 20% higher ampere rating than the maximum current drawn. So therefore we refer to the motor performance chart and we decide that a 30 ampere ESC is safe and can be used in this project. So next is the battery. So the battery, we use a max power graphene LiPo battery. So the specification is as shown. So the capacity is 2200 milliampere hour. The voltage is 4S and 14.8 volt. Discharge rate of 35C. So in order to ensure that the battery we choose is able to meet the requirement, so therefore we do some calculation and we prove that a 2200 milliampere hour battery is capable to meet the requirement of 5 minutes of endurance. So next is the servo. So the servo we choose is the Arduino Tower Pro SG90 servo. So the specification is as shown. So the servo we purchase is the servo quantity that we purchase is 4, because it is and also it is a like servo motor, so that's why we choose this servo. Next is the wiring system schematic diagram. So this diagram have graphically represent on how all the components that we select can be wired together, and also the voltage transfer is shown on the diagram. So next we will move on to the challenge phase. Is faced by our group is we lack of experience when in come of the selection of component. So therefore we concept to our lecturer a lot, and we also read a lot of tutorial online. Second, we have a requirement set, so therefore we need to ensure that the whole avionics system is able to support and reach the requirement. Next is the strength of our system. So how confident we are with our system. So first we have a tight collaboration with other group. So therefore there is a lot of detailed calculation to prove that our system is able to support the whole RC UAV. Next, we have purchased an all new and well functioned component. So I believe that it has a higher efficiency than the used component. And third is the setup is direct and simple, so it would be easy if there is any modification or repair in the future. So as for our weakness, I would say it is we lack of practical flight testing experience to observe the performance of the avionics system. So that's all for my presentation. Thank you.
Right, Assalamualaikum and good afternoon. My name is Muhammad Ashraf bin Abihan and I'm in a subgroup which is focused on the wing design. So this is my other group members, which is Alexander, Shafriz and also Wei Chin. So we start for the introduction of the subgroup, which is about the function of the wing. So first of all, wing is very important in our aircraft design which is because it is the most responsible part which to produce the lift while moving through air or some other fluid. And then wings also have the streamlined cross section that are subject to aerodynamic force and act as an aerofoils. Its efficiency is expressed as the lift to drag ratio, and the design or analysis of the wing of aircraft is one of the principal application of the science of aerodynamics, which is branch of fluid mechanics. It's so related to the fluid mechanics, which we have to do the analysis and we have to calculate how the lift and how the drag is produced. And next, to produce the lift, it must be oriented at a suitable angle of attack. So with a suitable angle of attack, the lift can be generated to lift the aircraft. The wing also deflect the airflow downwards as it passes the wing, and since the wing exerts a force on the air to change its direction, the air must also exert an equal and opposite force on the wing, resulting in different air pressures over the surface of the wing. And this is the simple diagram of an airfoil and how the lift and drag produced. Okay, we move to the next one, which is aircraft wing design. So in our aircraft design, we have choose to create a high wing configuration, which is we implement the high wing design by considering some of the factors, which some of them is high wing aircraft are generally less aerodynamic, slightly easier to train in for the new pilot, and also it is easier to access for routine maintenance than compared to the low wing aircraft. For high and low wing aircraft, there are some of the major difference, which some of them is in scope of lateral, roll stability, low speed handling characteristics, and also the general aircraft performance, such as cruise speed, takeoff, and also landing distance. High wing aircraft also increase the roll stability relative to the low wing aircraft, whose center of gravity is balanced above the wing. So it has some of the advantage, which is in roll aspect, it can have a higher stability compared to the low wing. And also the rectangular wing can also bring a lot of advantage, such as it can act as a wing root stallers. So this is part of the Federal Aviation Regulations FAR, which is a main wing located closer to the airplane's center of gravity than to the aft fuselage mounted and also empennage. A main wing that contains a quarter chord sweep angle and of not more than 50 degrees fore or aft. A main wing that is equipped with trailing edge controls, which is aileron or flaps or also both. And number 4, a main wing aspect ratio is not greater than 7. So this is our parameters of our aircraft, which is we are been using NACA 2412 for the airfoil, and we are having aspect ratio of 7.06, chord length of 0.17 meter. Our wing area is 0.20387 meter squared, and also our wingspan is 1.2 meter. The next one is the wing load analysis. So this is the progress of how we are doing the wing load analysis. So in this study, our RC plane is designed and analyzed, which we start with the sketch of how the airplane is envisioned. And next one is the weight is estimated based on the sketch that we have done, and also more refined method is conducted during this phase. And also the last one is to obtain a more refined estimation of the airplane weight. Several performance parameters must also be estimated. So according to the Federal Aviation Regulation, aircraft loads are those forces and loadings applied to the aircraft structural component to establish the strength level of the aircraft. So those are the loads that an aircraft structure must be designed to withstand. So for example, there are some of the part in the wing, such as rib and also spar, which we need to design the load so that the spar and the ribs can withstand the load, so it will not buckle or it will not fail during the flight. And the last one is the loads that must be determined early in the structural design. So before doing the flight testing, we need to do some calculations so that the part of the wing can withstand the loads. Alright, next, the greatest air loads on an aircraft usually come from the generation of lift during high G maneuver. So this is crucial as the aircraft might be doing a high G maneuver during the flight, and this is where the highest load will be applied on the part of the wing. So the amount of additional loads depends on the severity or turbulence. Its magnitude is also measured in terms of load factor, which is N. And other than that, at lower speeds, the highest load factor an aircraft may experience is limited by the lift available, and it is limited to some arbitrary value based upon the operation of the aircraft. So, in maneuvering envelope, the aircraft is assumed to be subjected to symmetrically maneuver, resulting in the following limit load factors. So, this is the load factor that we need to design for our aircraft design, which is the positive maneuvering load factor. The maximum one is 3.0 at speed up to V dive, and also the negative maneuvering load factor is negative 1.5 at VC, which is design cruising speed. So this process is then followed by the analysis of the wing parts such as spar, skin, rib, and also shear flow of the wing. So we move to the next part, which is aircraft airworthiness. The design process of an aircraft is regulated by the Airworthiness Authority to ensure the aircraft suitability for safe flight, and also the Federal Aviation Regulation Part 23 Airworthiness Standards. It is belong to normal category airplanes and is applied in our design process. So this is because there are some of the limitation that have been given for our project requirement, which is our maximum takeoff weight must be less than 5 kg. Our positive load factor is 3.0, and also our negative load factor is negative 1.4. So according to the Federal Aviation Regulation Part 23 Design Requirement and Specification, we are still below the limit of the FAR regulation, which is the maximum takeoff weight must be 5,700 kg. The maximum positive load factor is 4.4, and also the negative load factor is negative 1.76, which is 0.4 times positive N. And also the design airspeed is the limitation, it must be V dive must be more than 1.5 VC mean. So for the next part is assumption on the wing design. There are a few assumptions that have been applied on our wing design, which can be listed as follow, which is the first one is the wing is assumed to be a 2D wing, at which the factor of 3D wing design will not be taken into account. So this because for 3D case wing design, the calculation are more complicated, the analysis are more complicated compared to a 2D wing. So since this project are only given for one semester, so we need to take a 2D case, and it is more suitable compared to a 3D case. And the next one is the value of maneuvering speed must not be exceed the value of cruising speed VC used in the design, as stated before in FAR section 23.335. So we move to the last part, which is challenges and also weaknesses of our wing design activities. So during our workflow in our wing design analysis, there are some of the weaknesses and challenges that we notice which might affect the result of our design analysis and also calculation, which is the first one. The wing loading and structural analysis have been conducted under 2D evaluation, which lead to some factors are not be taken into consideration. This include the absence of the induced drag and also in our wing analysis. So as you can see, for a 3D case, we can take into account for the net downwash, which is the induced drag and also the wing vortices. But in our wing design, we are doing a 2D evaluation. So this is because based on the design and computational fluid dynamic analysis that have been conducted by Maria E. Ferguson, there are some of the differences in comparing 2D and also the 3D analysis, which is the 3D case had a higher maximum lift coefficient and also a higher stall angle compared to a 2D case, caused by the consideration of the induced drag. So this is very important, and this is giving a very large impact to our result because of the absence of the induced drag. It also includes the turbulence of wing, vortex, and also the pressure acting on the structure due to induced drag are not being taken as well in the wing of design analysis. Apart from that, in structure analysis scope, the analysis was based on the assumption of a simple structure. For example, the rib, the spar, and also the skin analysis, we are assuming it as a simple structure, so our calculation will be more easier and not so complicated compared to a 3D case. Flight tests should be conducted to validate and verify the calculations. So this is very important because of we have done the calculation, we have done the analysis, but we cannot validate the result whether it is acceptable or not. So flight test is one of the way that can be conducted to validate our calculation and our result, so that we can make sure that our aircraft can be fly safely without any failure. However, the wing analysis shows that the calculation for wing part are below the safety factor, giving an outlook of the wing can withstand the flight test. Even we didn't do the flight test to validate our calculation, but all of our calculation and results are below the safety factor, which shows that part of our wing will not buckle or will not having a failure during our flight. So that's all from me. Thank you.
Good day, Dr. Nazri and Dr. Wan Zaidi. My name is Alexander Jong Junwei. So I will represent my group, Wing Design, to explain the flight envelope and wing loading analysis. So as you can see over here, the figure shows flight envelope. So what is flight envelope? Flight envelope is the region within which an aircraft can operate safely. If an aircraft flies outside the envelope, it may suffer damage. The limits should therefore never be exceeded. To construct the flight envelope, the load factor limits are very important. They are +3 and -1.5 according to the project requirement and as per Federal Aviation Regulation FAR Part 23. Also, there are various important features of the VN diagram at point A, D, E, and G as indicated in the VN diagram. Point A, also known as the maneuver speed, defines the maximum airspeed that allows full maneuverability. At lower speeds, the structure cannot be overstressed because it will stall before reaching the limit load factor. The aircraft's limit load factor is reached at the maneuver airspeed. Higher speeds may result in possible structural damage. Also, point G defines the maximum airspeeds that allow full maneuverability in a negative lift situation. Airspeeds greater than point G give negative lift that can damage the aircraft structure. Besides, point D and point E, which also known as the dive speed, is the maximum speed before the aircraft enters the region where aircraft may experience structural failure. So as you can see from here, the speed at position A is 16.55 meter per second, while the velocity at point D and E are 33.6 meter per second, while the speed at position G is 16.3 meter per second. So now we look at the flow chart. Okay, from the load factor, we can simply determine the value of CL by using the equation as shown. Since assumption was made that the wing was a 2D wing, all the aerodynamic coefficients are obtained based on 2D wing analysis. So next, the section aerodynamic angle of attack, alpha, is determined from the graph of CL versus alpha graph for NACA 2412 as shown over here. Then, the aerofoil section lift coefficient CL and drag coefficient CD are determined from the graph shown here. The values will be substituted into the equation of Cn, which are derived from the resolving aerodynamic forces in figure on your left to find the lift force acting perpendicular to aerofoil at each station for point A, D, E, and G of the VN diagram. So after I have obtained the normal lift by substituting the value of Cn into the equation of normal lift, I need to obtain the shear load. How? First, by determining the changes in shear force, which is the delta Vn at each station, which is given by this equation, delta Vn. And after that, I need to obtain the corresponding shear force Vn at each station by summing up all the change in shear force delta Vn. Once this is done, then I will need to determine the bending moment. How? First, by determining the changes in bending moment, delta Mn, at each station as given by the equation, delta Mn. Once that is determined, then I need to obtain the corresponding bending moment, Mn, at each station just by summing up the change of bending moment. This is how I did the wing loading analysis without aileron. But what if there is aileron? So for the part with aileron, the wing loading analysis will be slightly different. Why? Because this is due to the change in lift coefficient, which is delta CL. Roll control can be achieved by the differential deflections of aileron. The deflection of aileron controls the increment of lift and the incremental change in roll moment. Downward aileron deflection will increase the lift coefficient value, while upward aileron deflection will decrease the lift coefficient value as shown in the flow chart. The deflection of aileron, either upward or downward, will affect the resultant normal lift acting on the aircraft's wing. So McCormick gives the following formula for the section lift coefficient increment due to aileron deflection, which is delta CL equals to CL alpha tau n delta. So how do I determine these parameters just from these figures? The figure on the left shows the parameters C, CF, and delta in aerofoil with plain aileron, while the figure in the middle shows the graph to obtain tau, flap effectiveness factor, by using ratio of CF and C. And the figure on the right shows the graph to obtain N correction factor from the deflection angle. Okay, so I'm going to talk a little bit about the deflection angle. For the deflection angle, position A and position G will have the same maximum aileron deflection, while on the other hand, the maximum aileron deflection at position D and E is the same. So based on roll control analysis to control the roll, when the critical speed is too high, the approximated maximum aileron deflection is 30 degrees at position A and G. But when the critical speed is lower, the maximum aileron deflection is approximated to be 10 degrees at position D and E. So when the aileron deflects downward, the total CL values will be original CL value plus with the delta CL at the angle of attack in position A, D, E, and G. But when the aileron deflects upward, the total CL value will be original value of CL minus the delta CL. So when you have a new CL value substituted into the Cn equation to obtain the normal lift coefficient Cn, so we can expect that the value of the normal lift will be different. And as a result, the value of the shear and the bending moment in each position will also be different. So how do I determine the normal lift, shear load, and bending moment? Similar as the wing loading without aileron. Okay, just by using the equation as shown over here. To get the shear load, simply by plugging all the values, while to get the bending moment at each station, again, by using the equation and sum up the change of the bending moment. So that's for the wing loading analysis with aileron. Now, I'm going to talk about the torsion analysis. So for the torsion analysis, it all depends on the value of moment coefficient Cm. So the value of moment coefficient Cm value can be obtained in similar way as how angle of attack is determined. So at each station, the Cm value can be determined from the graph on your right for point A, D, E, and G of the Venn diagram. Then the Cm value will be substituted into the torsion equation to obtain the torsion value at that particular position. The calculated results will be tabulated in tables for all the points A, D, E, and G, and then graphs are plotted. However, when there is aileron, or the part with aileron, there is a change in the moment coefficient. Therefore, the analysis will be different now. This is because the roll control of the aileron also affects the value of moment coefficient Cm. Now, the estimated change in Cm value can be determined from the graph on the left. So the figure shows that the graph shifts down when the aileron deflects with an angle of 60 degrees. But for our project, our maximum aileron deflection angle is 30 degrees for position A and G. Not just 30 degrees, but 10 degrees for position D and E. So for each of these maximum aileron deflection angle, I need to use interpolation method to obtain the approximated change in moment coefficient value. So from there, again, with the new Cm value, just plug into the torsion equation to obtain the torsion for the part with aileron. So that's not just it to obtain the bending moment diagram and shear force diagram. The reaction force for wing strut must also be determined. Why? Because the reaction force of the wing strut will affect the shear force diagram and bending moment diagram. So now to determine the reaction force of the wing strut, the wing loading analysis must first be conducted for half of the wingspan. So the problem simplification can be shown over here. The positive convention of the reaction force and moment that are indicated in the free body diagrams are shown in this figure. Okay, the aircraft wing is assumed to be a cantilever beam. The reaction force of the wing strut is indicated at point B, which is located at the middle of the wingspan. So the horizontal reaction force, Rxa and Rxb, will cancel out each other at the end of the calculation. During the initial stage of design, since the wing weight is smaller as compared to other components of the aircraft, the weight of the aircraft can be assumed to be concentrated at point A. And that's how I get the applied load, which is indicated with the orange line shown in the free body diagram after simplification. That is the total concentrated weight of the whole aircraft. So now after neglecting Rxa, Rxb, and also concentrating all the applied load at the center, the problem is a statically indeterminate structure. So how do we solve this? Is by using flexibility method according to the Castigliano theorem. So now the system has three reaction forces as shown in the figure, Rya, Ryb, and Ma. So I need to determine the degree of statically indeterminate structures. How? Through this equation as shown. Q represents redundancy, and the equation below shows the general equations of the flexibility method and their respective name of parameters. So with the angle between the wing strut and the wing, we can obtain the reaction force of the wing strut as given, which is 84.56 Newton. So after calculating the normal lift force, shear force, bending moment, and torsion from the wing loading analysis with aileron and without aileron, the values are tabulated and presented in graphs. So these two figures are the graph of normal lift across wingspan. But the figure on your left shows the normal lift force across the wingspan when it was zoomed in to a smaller range of normal lift force axis, while the figure on your right shows the normal lift force across the wingspan when it was zoomed out. Now, when you look at it, there's a sudden spike of the graph. Why? Because this is due to the reaction force due to the wing strut, which we assume to be a concentrated load force at a small area, as I mentioned in the previous slides. So in both figures, the normal lift force is a constant straight line, since the wing is assumed to have no twist angle due to its small size, and the angle of attack is constant across the wingspan without aileron. However, there's a slight change in the normal lift force at a distance of 0.4 meter away from the wing root, or when the 2y over v is around 0.64. That is where the aileron is located on the wing. So the change of the normal lift force is due to the aileron, which resulted from the change in the lift coefficient that I have already discussed in the previous slides. As the aileron deflects downward, the lift coefficient increases, and hence the increase in normal lift force, and vice versa. Next, these figures are the graph of shear force across wingspan when the aileron deflects downward and deflects upward. So the graphs are almost similar, as you can see over here. This is due to the reaction force of the wing strut that supports the wing. The sudden change in the shear force in the graph indicates where the wing strut is located. As a result, the shear force diagram differs from the normal shear force diagram that we know, which shows a graph with a decreasing slope along the wingspan. The difference between both figures, as shown here, is that the maximum shear force is relatively smaller when the aileron deflects upward in the figure on the right. Yes. This is because the change in lift coefficient when the aileron deflects downward is larger. It all depends on the change in lift coefficient. Next, both of these figures show the bending moment diagrams that are affected by the reaction force of the wing strut too. The bending moment diagram and shear force diagram are derived from the normal lift force diagram. As shown in these figures, the bending moment is negative when the load factor is negative and vice versa. Also, difference between both figures is that when the aileron deflects downward, the moment of reaction and the wing group is positive, and when the aileron deflects upward, the moment of reaction and the wing group is negative. This is to counter the opposite direction of the applied moment on the wing. So now look at this. The figure on the left shows the graph of torsion across the wingspan. As I've already mentioned in the previous section, the value of torsion depends on the value of moment coefficient, Cm value. The change in the Cm value, moment coefficient, is due to the aileron deflection. and it still depends on the position of the wing during flight. Position A and G in the VN diagram experience polar angle deflection of aileron than position D and E. Why? Because of the maneuverability and control of the aircraft at lower speed. Therefore, the change of torsion is relatively smaller at position A and G. When the aileron deflects downward, the torsion decreases as the moment coefficient decreases. The amount of change in moment coefficient, again, depends on how much the graph of Cm versus alpha graph is shifting downwards. So on the other hand, the table on your right shows the maximum shear force is 14.3394 Newton at position D when the aileron deflects downwards. As the shear force is the highest, we can expect that the value of both the bending moment and torsion at position D is also the highest. This is because the speed and the log factor are the highest at position D as compared to other positions. The shear force and bending moment at position A and D are higher as compared to position E and G. This is because the magnitude of positive log factor of aircraft at position A and D is larger than the negative log factor of aircraft at position E and G. Positive 3 is larger than negative 1.5. The maximum shear force, maximum bending moment, and the maximum torsion are very important because they will be used in the structural analysis conducted in the next few sections in order to determine if the wing structure is safe or not. That's all from me. Thank you.
Assalamualaikum and hi everyone. My name is Muhammad Shafiz bin Matshaiful, and now I would like to talk about the structural analysis of the wing for group 2. First, I will explain the material of the wing that will be used in this project. For the rib of the wing, we are using plywood material. For the skin, spar and aileron, we are using EPP foam. Here are the material property for the EPP foam and plywood, which will be further discussed or used in the analysis. The modulus of elasticity, the yield strength, the ultimate tensile strength, the shear strength and the density are stated in this table. Here is the thrust calculation for the spar. The loading on the spar will be shear and bending. From this diagram, the spar is located here in the middle of the wing part with the dimension of 60 cm. For the spar, there will be shear stress loading, which is the equation my/I, and also the shear stress loading equal to V/A. The value for the moment and also shear stress is obtained from the previous analysis, which are taken for the maximum moment and also maximum shear, and then we are calculating for the critical buckling strength, which will further be using to calculate the factor of safety. Here are the analysis for the rib. The rib has been divided into two sections. For the front part, which is in front of the spar, it's known as cell 1, and for the back of the spar is cell 2. The pressure underneath the airfoil is higher compared to the pressure upper side of the airfoil, thus will produce a lift. From this diagram, we are knowing that the lift distribution for along the airfoil is like this one. Here are the divided cell. This is the cell 1 and this is the cell 2 lift distribution. For the real cases, the graph for the lift distribution is more complex, but in our case, the wing is small, so we can simplify the problem to this kind of graph. Okay, so now here is the stress calculation of rib continuation. From this diagram, we can see that the rib within the wing are located in 4 places, which is in the location 1, the location 2, location 3, and location 4. Location 1 until 2 we call it bay 1, and then for the middle part is bay 2, and then for the rest is bay 3. For the calculation of the wing loading in the previous slide, we calculate the wing loading by using the total area of this distribution. Based on the graph of normal lifting force across the wingspan, for the bay 1 is 13.8393, and for the wing distribution we get is 46.5187. As the bay 1 and bay 3 is assumed to be equal, so we only do the analysis for bay 1 only, and then for the bay 2 the normal lift is 36.5136, and the load distribution is 89.1213. For the bending moment due to the air load, the equation for the moment of cell 1 will be used with this equation, and this is the moment for the cell 2. Same goes to the shear. This is for the cell 1 and this is for the cell 2. And then we are using this parameter, minimum moment and shear, into the loading formula, and then we also calculating for the critical strength, which further will be finding for the factor of safety. Okay, here are the results that we obtained from the rib analysis. Here we are seeing the shear force across the chord. The shear force is decreasing along the chord, and also the bending moment get the same result, which is decreasing along the chord. The trend of both diagram depends on the lift distribution across the chord, which is in reference to FAR part 23. Here is the skin analysis. The loading on the skin are divided into two parts, which is upper skin and also lower skin. For the upper skin, there will be a combined shear and compression experienced by the upper skin, and for the lower skin is combined combined shear and tension. Here there will be a compression, and here at the downside will be tension occur. Same goes to the previous analysis. We are calculating for the loading by using shear stress shear bending equal to M over I, and social stress equal to V over A, and then we are calculating for the strength, critical buckling, and then we are obtaining for the factor of safety by using this formula. Here is the shear analysis for the single cell section. The shear flow has two part, which is due to shear and also due to torsion. For the due to shear, we are using tau equal to Q over T, which is the Q is shear flow and T is the thickness, and for the torsion we are using this formula. From this diagram we can see that around the airfoil will be shear flow, and with the arrow indicate upward is for the shear flow due to shear, and for the this arrow indicate the shear flow due to torsion. Later we will sum up the total of the shear flow due to torsion and due to shear to get the factor of safety. The stress calculation for the skin, Okay, the analysis for the skin, we are taking the positive deflection and also negative deflection. The flow for the calculation is, first of all, we will calculate the shear flow, which is represented with Q. Vs is the shear in this example is due to the shear, so Vs is the maximum shear. If the due to torsion, we will taking the maximum torsion, and then after we get the shear flow, then we will calculate the shear stress by using this formula, including the shear flow in this formula divided by thickness, we'll get the shear stress. And then we will calculate the safety factor for the cell by using this formula. Fs is the maximum tensile strength, and tau b max is the maximum shear stress from this equation. Here are summarize of the effective factor. Here are the summarize of the factor of safety for the analysis. For all structure, we can say that the value of the effective factor of safety is more than 1. Thus, it is assumed that all structure within the wing is safe to operate. Okay, here we will discuss about component attachment and fitting. For the attachment of the wing with the body, we will use a gypsum screw. As we can see from this diagram, we will be putting or install the gypsum screw in 4 parts. Then we are using the hot glue gun to attach the spar and also the rib to the wing skin, and finally we will using a fiber tape for the attachment of the aileron with the wing skin. Here are the part attachment for the aileron and airfoil. From this diagram, here is the load distribution for the airfoil itself, and here is the load distribution for the deployed aileron. So it is produce moment and also shear stress. This is the load distribution across the chordwise. For the calculation, we referring to the Federal Aviation Regulation FAR Appendix A to Part 23. The simplified limit surface loading for the aileron is specified as this diagram. So from this diagram, we use this formula in order to get the load distribution for the part attachment. Here are the results that we obtained from the analysis. For the load distribution, we get 23.7127 Newton per meter, V is 0.4743 Newton, and moment is 0.0063234 Newton meter. Here is the part attachment for the wing strut. We will using wing strut to attach the wing and also fuselage to make sure the wing are not being deflected too much and also stay in its position. For the wing strut, we are attaching it with a 45-degree angle to the fuselage wall and also to the underside of the wing. For the wing strut, we will be using glue to attach the wing strut to the wall of the fuselage and also to the wing by indicating with this red color is the area for the wing strut to be glued. And then we are using a fixed hinge with a slight angle for the attachment of the strut with the wing and also fuselage. Hinge pin is used to give an extra support to the wing strut, and then we are using a hinge pin to make sure that there will be no movement to the fixed hinge horizontally. And for the fixed hinge, we are make sure the wing strut will not be moving in the horizontal direction. The material selected for hinge and the hinge pin are mica plastic and AN steel respectively. The moment at the joint is assumed to be 0 at the initial design stage. Thus, the wing strut is a 2-force member with pin joint at both ends. Since it is a 2-force member, so the analysis taking for the wing will be the same as the analysis taking at the fuselage area. So we will be conducting only one area in the analysis of the part attachment of wing strut. Now we will go through the manufacturing process of the wing. The apparatus for the manufacturing process of the wing, we will be using hot iron, fiber tape, heat gun and metal pipe, CA glue and also solder. For the wing skin component, we are using 5mm EPP foam. We are cutting the 5mm EPP foam according to the wing size, and then we are folding the EPP foam to get a airfoil shape of the wing. And then for the spar, we are using 5mm EPP foam and also 3mm plywood. The spar we will be installed inside of the skin with the help of the plywood to be attached together with the spar to get an extra strength. And then for the rib, which is in airfoil shape, we are using an airfoil former by drawing the airfoil shape on a paper, and then we are cutting the plywood according to the drawing that we had been drawn on the paper. For the wing tip, we are using 5mm EPP foam and also sandpaper. 5mm EPP foam, we are using 4 for the left side of the wing and another 4 for the left side, for the right side of the wing. And then we are using sandpaper to get a smooth surface for the wing tip. And then for the aileron, we are using a 3mm EPP foam taking from the wing skin itself. We are cutting the aileron according to the aileron size from the wing skin, and then we are using the cutted aileron by using fiber tape to attach the aileron with the wing skin to allow the aileron to be deflected upward and downward. For the wing mounting, we are using 3cm gypsum screw, 5cm gypsum screw and black decal. The function for the black decal is to mark the position for the screw. And for the electrical component, we are using 2 servo, 2 wire and 2 rod. The servo are using to give the force to move the aileron upward and downward. For the wire is for the electrical transmission from the battery to the servo, and for the rod is to transfer the energy from the servo to the aileron so that the aileron can be pushed and pulled to make it deflect upward and downward.
Assalamualaikum and good day to the lecturers. Today I, Muhammad Hafiz Akmal, and my group will present to you about tail and fuselage design. So firstly, I will introduce my others member of my group. First is Ahmad Fakurati and the others is Muhammad Hanif Shah. Firstly, weight and loading for aircraft. The maximum take-off weight for our aircraft design is 1,500 plus minus 100 gram, and the empty weight is 1,000 gram. Based on the table, we can locate the location of each type of the component that been used in the aircraft. So for our fuselage design, we use a fuselage monocoque structure, which is relies largely on the strength of the skin to carry the load, and the monocoque structure consists of former, frame assembly, and bulkhead to give a support to the fuselage. And the heaviest of the structure member are located at interval to carry concentrate load and at point where fitting are used to attach other units such as wing, power plant, and stabilizer. You can see that the design is quite simple and easy to fabricate. For tail design, we use conventional tail. Its most common use for RC plane is foam. It can provide adequate stability and control with lowest structural weight and low risk and ease of control and manufacturability. So the challenge and weakness in the fuselage design is the fuselage scheme may not be able to withstand the weight of other components, and it will affect the skin to bend. Next is the location of the concentration stress on the fuselage skin. With these two challenges, the solution we must use is by using structural analysis and shear bending diagram to know the material for the fuselage skin is suitable for the aircraft or not. And the fuselage skin, former and bulkhead material also can be affected if the material does not suitable for each of their function. Next is fabrication of the fuselage is quite difficult because in the design we can see that the fuselage is quite curved, so to fabricate the curved part require a more skilled hand to fabricate it. Next challenge is the fuselage may undergo a crash because of impact during the landing. So to solve this problem, we must give the piloting to the skilled pilot, not the first time pilot. Next is shear force and bending moment diagram for fuselage. So in the cruising condition with G equal to 3, the velocity is 14 meter per second. You can see that the shear force, maximum shear force is 19.24 and the bending moment is negative 1.44. Next is cruising condition for G equal to 1 with the same speed. The shear force is 6.4 Newton and the maximum bending moment in this cruising condition is negative 0.48. Next is cruising condition in G equal to negative 1.5. The shear force maximum is 5.37 Newton and the bending moment maximum is 0.7 Newton meter. So with the shear bonding diagram, firstly we must know the material properties of the material we use in the fuselage. So in the fuselage we use EPP foam. The ultimate stress is 27.57 megapascal and the thickness we use is 0.005 meter. With the material properties, we can calculate the maximum bending moment for the foam that can withstand. So the moment maximum is 1.951 kilonewton meter and the shear force maximum for the foam is 67.83 kilonewton, and we can see that the maximum bending moment and maximum shear force is in range of maximum shear force and bending moment of the foam. So overall, during the cruising condition, the APP foam will not diminish easily. Next is the shear flow of fuselage due to torsion. The torsion we get during the cruising is 1.119 Newton meter, and by using the torsion we use the formula torque equal to summation of 2ARQR. R which mean is the number of cell, so we can get Q1 equals to 9.225 Newton per meter, Q2 equal to 13.915 Newton per meter, Q3 equal to 6.7869 Newton per meter. Then by using the Q, we can get the shear stress for each of the cell. Cell 1 shear stress is 9.558 kilonewton. Cell 2 have shear stress equal to 11.257 kilonewton, and cell 3 have negative 1.019 kilonewton shear stress. With the shear stress, we can calculate the safety factor by using Fs equal to shear stress. Fs is for the EPV form is 13.785 megapascal. So SF safety factor for cell 1 is 1442. Safety factor for cell 2 is 1226, and safety factor for cell 3 is 13,528. So we can see that all cell obtain safety factor that exceed 1, so all cell can withstand the torsion within the aircraft cruising, so the skin does not damage. That's all for me. So I will pass this next slide to the Ahmad Fakrul Razi.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Fakrul Razi bin Abdul Latif, and I will start my presentation with SolidWorks flow simulation on our RC plane. I use the maximum speed of our RC plane, which is at 3.6 meter per second, to see what happened to our RC plane when it fly with maximum speed. Since the flow is not based on the real case, the result here is just an estimation. The reason why I say it is not based on the real case, because in real case there will be an external forces that may face by our RC plane, for example wind, and everyone knows that wind have various speeds, so we cannot know how many amount of speed the wind will give to our plane. So now moving to the purpose of this flow simulation. The purpose is to estimate the pressure applied on the fuselage surface. In specific, I interested in the region where the former and bulkhead structure is located, which is here, since after this I will focusing based on these two structure. And finally, during the simulation, I found that the upper surface of the wing experienced vorticity flow near the attachment location. For structural analysis, I use ANSYS in order to obtain the stress gained by the structure, and this figure is shown on how the load is applied on the former surface, on the former structure. There is additional load acting here, which is from the weight of the wing. These both figure here show that the pressure counter of the both equivalent and shear stresses, and for both equivalent and shear stress, the pressure counter show that most of the structure managed to have maximum stress. And for more detail on the value of the stress is shown in this table here. Same as the previous slide, bulkhead structure analysis was done by the ANSYS, and this figure show on how the load is applied on the bulkhead structure. These two figures show the pressure counter of the both equivalent and shear stresses. And for both equivalent and shear stresses, the pressure contour show that most of the structure managed to have minimum stresses. And also for detail on the value of the stress is shown in this figure here. I mean this table here. To check whether the structure will buckle or not, compressive buckling analysis was done using this equation, which is taken from the Brun, and this equation is used to calculate the critical compressive stress of the structure. And this is how critical compressive stress and margin of safety was calculated. So first we will go to the calculate the aspect ratio of the former, and then from the graph compression buckling coefficient, based on the we can find this graph from the Brun, and we get the value of Kc and substitute all the value into the equation, and we'll get the value for the critical compressive stresses. And to find the safety factor, we use this formula, which is critical buckling stress that we get from this is divided by the maximum stress that we calculate in the result from the ANSYS. And to find the safety margin, the safety factor need to minus by 1 to get the value. And since the compressive critical stress is larger than the maximum stress from the ANSYS result, the former structure will not buckle. And since the value of the margin of safety is positive, therefore the structure is safe. And this also same method as previous slide, but for structure, bulkhead structure, the bulkhead structure will not buckle because the critical stresses is larger than the maximum stress. And same goes to the margin of safety. The structure is safe since the value of the margin of safety is positive. And for shear buckling analysis, the method is quite similar to the compressive buckling analysis, but with different equation is used. And this equation is used to calculate the critical shear stress of the structure. So this is the result of the calculation, and the result of the calculation found out that the former structure is safe and will not buckle since the critical shear stress is larger than maximum shear stress. And same goes to the bulkhead structure. The result of the calculation found that the structure is safe and not buckle since the critical shear stress is larger than maximum shear stress. And for the last words, both former and bulkhead structure is safe and will not buckle whether in compressive or shear. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hanisha bin Khairul Anwar. Here, I would like to present about the challenge and weakness that related to the tail design. As we know, the function of the tail is to improve the aircraft stability. Same goes to the RC aircraft. There are several challenges that have to be considered in the process of design. First, horizontal tail surface may not able to withstand the stress that experienced during cruising. Second, during cruising, horizontal tail may damage caused by the pressure. And the last one is the crash on the tail as the impact during landing, either safe landing or emergency landing. The solutions that can answer towards this challenge are by doing structure analysis, shear bending diagram, and the last one is, of course, it is depend on the piloting skill. Okay, first, as we look to the structure analysis on horizontal tail, Here is the picture where the simulation has been done by using SolidWorks, the flow simulation with the speed of wind 33.6 meter per second, and the rotational speed is 860 rpm. Okay, the stress on the surface has been taken on maximum and minimum for horizontal tail and vertical tail. So the maximum value written here and maximum here. So as we take the overall maximum value and minimum value times by 1.5 factor, we get this force, the stress of the ultimate for minimum and maximum. Okay, next, by doing this structural analysis, we refer to Broom book. The element taken from the tail for A over B is 2.5. Using this graph, shear buckling stress coefficient is 6. By applying the critical stress formulation here, we obtain that the critical stress is 37.38 megapascal. F0.7 is calculated to be used in the correction method later. In this correction method, take the minimum number of n, which is 2, using the graph of chart of non-dimensional compressive buckling stress from the calculated critical stress divided by F0.7. Referring to this graph, the new plastic critical stress is 1.3. Then it is multiplied with F0.7 as we get 35.84 megapascal. Safety factor and margin of safety are given by this formula. From this calculation, margin of safety, it is stated that greater than 0, which indicates that both of maximum and minimum value will not buckle. Here is the shear and bending diagram for tail. Apply for G equals to 1. Then here is G equals to 3. And the last one is G equals to negative 1.5. They have different trend of graph and amplitude. The maximum values of shear force and bending moment are shown in table here. As we calculating the maximum bending moment that can be stand by this foam, we get the maximum moment is 2.06 Newton meter. By applying shear force for this condition, we get the maximum shear stress is 201.03 Newton. So, ultimate stress from the foam shows that maximum shear force and bending moment is 201.03 Newton and 2.06 Newton meter respectively, while the maximum shear force of 0.5985 Newton when G is 3 and maximum bending moment 0.1734 Newton meter when G is equals to negative 1.5. So, in conclusion, both of its value within the range of maximum shear force and bending moment of the foam, then we can say that it is safe.
A very good day to you all. My name is Cheng Wei Ching. I'm going to talk about landing gears. The landing gears part for our RC plane is steel wheel type landing gears, which is an aircraft undercarriage consisting of a main wheel forward of the center of gravity and two backward wheels to support the tails. It's known as conventional landing gears. The term conventional persists for history reasons, but all modern jet aircraft and most modern propeller aircraft use tricycle gears, with a single nose wheel in the front and two or more main wheels aft. The tail wheel configuration offers several advantages over the tricycle landing gears arrangement, which make dual-wheel aircraft less expensive to manufacture and maintain. There are two formulas to calculate the static load analysis, which is maximum static main gear load per stroke and maximum static nose gear load. And this is the diagram for nose landing gear load calculation. And this is the figure for center of gravity for nose landing gears. And this is the information that required. And this is the result for the maximum static main gear load, which is 0.03195 Newton, and the maximum static nose gear load is 0.03115 Newton. So next is the introduction of finite elements method. FEM is a fundamental numerical procedure for the analysis of structures. It's a numerical method for solving problems of engineering and mathematical physics. The use of the numerical methods to solve mathematical models of a complex structures has become essential criteria in design process. It has been widely used to solve engineering problems in visualizing the stresses and displacement of a model. It provides an outcome of finite elements analysis, which is able in turn help in producing a better products to an industry company. Next is the software used, which is Abacus. Abacus is a commercial software to be used in order to conduct the simulation in finite element analysis. It also contains a vast library of elements that can model virtually any geometry. It has an equal extensive list of material models that can simulate the behavior of most typical engineering materials. And this is the material properties for landing gears. There are two components, which is attachment of fuselage and support. The material used for the attachment of fuselage is plywood and stainless steel for the support. And this is the specifications and parameter for both materials. And this is how I apply the load on the front landing gears. For the static analysis just now, I get the value and I divide the area of the attachment of the component that I can get the pressure. So this is how I apply the load. For the boundary conditions, I fix both ends, so they are fixed support. So about the meshing, the approximate global size is 2, so 1,292 elements has been generated on the landing gears, and the element used is tetrahedrous elements. So this is the result of the finite elements analysis, and this is the undeformed shape. So next one is the contour plot, and this is the one minus stress. For the red color is the highest stresses and the blue color is the lowest stresses. So for the both end, as you can see at the curve place is red color, which means it's critical stress at the curve area and the fixed support area. And this is the magnitude displacement, and this is same as the one minus, which is the red color is the most critical and the highest magnitude, and the blue color is the lowest magnitude. As a conclusion, the main function of the nose landing gears is to balance the aircraft and provide it with ability to steer when plane is grounded. The major material of use in the landing gears is stainless steel because of the characteristic of itself has higher yield stress to withstand the 90% of load. From the result obtained by using Abacus, undeformed shape is the situation where there is no force acting on it. When 0.03195 of load was acting on the front landing gears, it began to deflect downward and deform shape of the landing gears. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azamuddin bin Muhammad Tahir, and now I'm gonna present about the center of gravity and the stability for our RC plane. So let's take a look on the center of gravity first. As we know, there are 4 types of CG, which is the empty weight CG, maximum weight CG, forward CG, and aft CG. And this we will show the calculation for this type of CG. So, but before that, we need to determine the CG location of each component on the aircraft. As we know, there are a lot of components that we put in it, such as the propeller, the receiver, the payload, and all the other components. Then we need to put a reference point that we can measure from, which is, in our case, we put it here at the tip of the propeller. So the distance, for example, the distance for CG motor is this. This is the distance. Okay, so now let's calculate the empty weight CG. But first, we need to list down all the components that involve in empty weight, such as the propeller, motor, wing, and all of this. And we need to put the mass of it. And to calculate the moment, we need to times the weight with the distance, and we can get the moment for each component. And we can sum up the component, we can sum up the moment. And in order to find the CG for each, for the horizontal CG, we need to divide this, the total moment and the total weight, and we can get the horizontal distance for CG. And for vertical, we do the same thing. And as you can see here, there's a negative value, which is, okay, since we put this as a reference point, so everything that go up is positive, and everything that is located below this point is considered as negative. Okay, so this is the CG value, the horizontal CG for empty weight, and this is the vertical one. So we do the same thing on the maximum weight CG, but this time we need to include the payload. And as you can see here, the location of CG has changed a little bit, but it's not that much. From here, this is 278 millimeter, and this is 283 millimeters. So the empty weight CG that we have calculated before is located in front of the payload CG, and from this we can conclude that the aft CG is equal to maximum weight CG, and the forward CG is equal to empty weight CG. So this is the total, all the location of all CG on the aircraft. There are 2 points, since the forward CG and empty weight CG is located at the same point, and aft CG is located at the same point with maximum weight CG. Okay, so let's take a closer look on it. There's a difference between these 2 points actually, but it's not that much. So that's for CG, and now we move on to stability. So in general, there are 2 types of stability, which is the static stability and dynamic stability. And in each category, there are 2 types, which is the longitudinal and lateral. So I'm gonna explain about longitudinal, and the lateral will be explained by other group members. Okay, so let's take a look on the static stability first. But before that, we need to define the static stability, which is the initial tendency of an aircraft to return to its original position when it's disturbed. So as we can see here, there are 3 types of static stability, which is the first one is the equilibrium flight, where during the flight the lift is equal to weight, thrust equal to drag, and no net moments produced on the aircraft. And the second one is we consider as statically unstable airplane, where when it flies in an equilibrium condition and it is disturbed by some wind or gust, and it cannot go back to its original pace, and it continuously rotate in this way, and this is not good for our aircraft. And the third one is the neutral static stability, and when it's disturbed it cannot go back as well, but it stay at this position. So this is also not good. We need to find the static stability for our aircraft. So in order to find the static stability, we need to recognize the moment on the airplane. So from this figure, there are a few forces that contribute to the moments on the airplane, and we need to find the moment about this CG location, which is created by the lift of the wing, the drag here, and the moment produced at the aerodynamic center, and the lift of the tail, and finally the thrust. And from here we can see that the weight of the aircraft does not contribute to the CG, since it is exactly on CG location, so it does not contribute any to the moment. So this is the pitching moment coefficient about the CG location is defined as, this is general formula of it, Cm is equal to m over the dynamic pressure time with area and the chord length. And an airplane which is in equilibrium, an airplane is in equilibrium when mcg is equal to cmcg and it is equal to 0, which means there are no moments. So in order for us to get a statically balanced airplane, we need to have this kind of figure for our Cm alpha graph, which this is the general graph for Cm alpha, where the slope must be negative and the intersection point here Cm naught must be positive, where Cm naught is the CmCG at 0 lift. Okay, so let's take a look on the calculation for slope of moment coefficient curve Cm alpha. So this is the general formula for it, and we just need to plug in the value that we have obtained earlier in this equation, such as the A, which is the lift curve slope, and which is 0.1066 per degree, and H is the location of center of gravity that we have obtained earlier in the CG part, and the HACWB is defined as location of wing body aerodynamic center, which is 0.274, and VH is the tail volume ratio, and this is the value we get from the drawing is 1.276, and the AT is defined as the tail lift curve slope, which is 0.106 per degree. And this for subsonic flow, we get the value is 0.0102. Since we have two different CG locations, so we need to do two different analysis, which is the first one is where H is equal to 0.278, which is for empty weight CG, and the lift curve slope, and the moment curve slope is negative 0.133, and for maximum weight is negative 0.132. So now we need to find the Cm naught value, where Cm naught is the CmCG at 0 lift. So this is the general formula for it, and in our case CmAC wing body is equal to 0.228, and VH is defined as the tail volume ratio, which is 1.276, and AT is the tail lift curve slope, 0.106 per degree, and IT is the tail setting angle, which is 7 degree, and downwash angle at 0 lift is equal to 0 degree. And therefore we need to plug this value in this equation, and we get the Cm naught value is 1.175. So after we get the two value, we can substitute the value in the linear curve for moment coefficient versus alpha graph, which is this equation. And by plugging in the two different values, and for empty weight we get this equation, and for maximum weight we get this equation. The difference between these two equations is just the slope, and we can plot the graph for two different type of CG, and we can get this kind of graph. So as you can see here, there are slightly different between these two locations. Okay, let's take a closer look on it. Yep, but it still fulfill the requirement for us statically for directional stability. So the equilibrium angle of attack was obtained from we need to find this angle of attack, and we get the equation, so we just need to put the Cm equal to 0, and here you can see that the alpha is 8.9 degree, which is the trim angle. So apparently the angle of attack fall within the reasonable flight range, therefore the aircraft is longitudinally balanced as well as statically balanced. So let's take a look on the neutral point. So neutral point is a specific location of the CG where Cm alpha is equal to 0. So neutral point is denoted by -n. So in this figure we can see the effects on location of center of gravity relative to the neutral point on static stability. So we can calculate the neutral point for our RC plane by using this general formula, and by substitute the value of this parameter into the equation, we get the Hn is equal to 1.5298 meter. So by comparing the H, which is the location of CG that we got earlier, which is it is obviously that H is less than Hn. Okay, for reference, the H that we obtained earlier is this value 0.278 and 0.283, which is less than 1.5298. Okay, let's take a look on static margin, where static margin is defined as the distance between the CG and the neutral point. So we just need to find this distance, and for our aircraft, for empty weight CG, the static margin is 1.252, and for maximum weight CG is 1.2468. So from the calculation of the static margin, the value is positive in all CG location, and hence the aircraft is statically stable. We can also conclude that the degree of static stability is high due to the large value of static margin. Okay, we are done with the static stability. Now we move on to dynamic stability. And dynamic stability is concerned with the time history of the aircraft motion after being disturbed from its initial equilibrium condition. And a statically stable aircraft does not guarantee it is a dynamically stable, but a dynamically stable aircraft is for sure it is statically stable. So in order to find the dynamic stability, we need to use the state space matrix, where this is the general state space matrix, and for longitudinal motion the state space matrix is xu, xw, and this is the general one, where u is the velocity in x direction and w is the velocity in z direction, q is pitch rate, theta is the pitch angle, and delta E is the elevator deflection. So these are the derivatives or in order to find the state space matrix, and by plugging in this value into this equation, we get by taking the flight case for our RC plane flying at sea level and at a velocity of 14 meters per second. So this is the state space metric for longitudinal motion due to the elevator deflection. And from this equation we can get the state space matrix, which can be written in the form of transfer function. So this is the transfer function, and it all has the same characteristic equation, where from the characteristic equation, all the sub value of the representing the phugoid and short period is positive in its value, which means it is in a stable condition. So by using MATLAB, we can plot the time response for 50 seconds, and this is the result. So as we can see here, let's take a look on closer look. So this is for u, which is the forward velocity, and this is for w, q, and also theta. So forward velocity in phugoid mode, u is having a large damping ratio here due to long period oscillation, while w and q are having a lower damping ratio due to the short period motion. And the state space metric then reduced to short period motion, where the matrix and transfer function are shown below. And for short period motion, we can also have its own transfer function, and again the characteristic equation will remain the same for these two transfer functions. and this is the time step response for the short period motion, and this is for A, and this is for Q, which is the pitch rate. And using MATLAB also, you can get the damping ratio and the frequency. And from the open transfer function of short period motion, it is shown that our aircraft is having a low stability condition where the damping ratio is 0.557, where the good one is about 0.7, and the natural frequency is about 10.2. So our RC plane are considered as not dynamically balanced, but it is a statically balanced plane. So that's all from me. Thank you.
Good day. I meet to Dr. Nazri and also Dr. Wan Zaidi. My name is Shama Devi and I am from Group 2 who would like to present on the dynamic lateral stability system. So before that, I would like to give the definition of the lateral stability. Lateral stability is the stability displayed around the longitudinal axis of the airplanes, and airplanes at times will return to a wing level altitude after being displaced from a level altitude by some force, such as turbulent air, is considered to be laterally stable. So for this project, the analysis of the lateral stability, I have used the method of what I've learned in my flight dynamic class semester. So as we can see on our right, is the lateral state space equation, which we have x equals to ax plus bu, where beta is the side slip angle, p is the roll rate, and r is the yawing rate. Phi is the bend angle, delta A is the aileron deflection, and delta R is the rudder deflection. So in order to occupy the unknowns in matrix A and also in matrix B, we need to find three different coefficients first, which are the side force coefficient derivatives, yawing moment coefficient derivative, and the rolling moment coefficient derivative has been displayed in the left hand side, the table here. So these values are actually obtained from Cessna 172. I've made some adjustment and also some assumption for the UAV Cessna 172. So after obtaining all these values, and then we can substitute into this lateral directional derivatives. So we substitute all the values that we get before the three coefficient derivative, we substitute into here, and then we'll get on the right, we can see, then we will get this lateral directional derivative, which can be seen on our right. So after we've obtained all these lateral directional derivatives, and then we substitute into back our matrix. So from the state space equation, by using a MATLAB program, the transfer function of the lateral motion is obtained. The stability of the aircraft is able to determine from the transfer function. So we have inserted all the values. So this is the steady state equation that is obtained. So the transfer function of lateral motion is divided into two. One is for the aileron input, and another one is for the rudder input. So we have 4 transfer function for the aileron input and also 4 transfer function for the rudder input. As we can observe, the denominator of each transfer function are the same. So the denominator of the transfer function is known as the characteristic equation, which is shown below. Hence, from the characteristic equation, we are able to find the natural, the spiral, and the roll. And from there, from the natural, spiral, and roll, we can able to find the damping ratio, the natural frequency, and the time constant. And then we can able to find the flying qualities of the aircraft. Flying qualities of the aircraft are related to the stability and control characteristic. It can be used to describe the stability and control characteristic of an aircraft for given cases, which allow the pilot to give opinion to the level of flying qualities. The flying qualities can be classed into three levels, which are level 1, level 2, and level 3. The flying qualities depends on the type of aircraft and flight phase. The type of aircraft The flying quality depends on the type of aircraft and the flight phase. The type of aircraft is classified into 4 classifications depending on the size and the control characteristic. Flight phase is characterized in 3 different phases depending on the terminal or non-terminal flight. For our case, the UAV case, which we are using Cessna 172, is classified as Class 1 airplanes as it is small, light airplanes such as utility, primary trainer, and light observation aircraft. This plane is categorized as a non-terminal flight under Category C, which is gradual maneuver and accurate flight. So as we can see, for ratio, we have obtained the flying qualities, which is level 1, spiral, which is level 1-2, and for drone, which is level 2. Both spiral and Dutch mode have the same flying qualities, which is level 1, where the flying qualities clearly indicate for the mission flight phase. For roll mode, it is level 2, where the flying qualities indicate to accomplish the mission flight phase, but with some increase in the pilot workload and degradation in the mission effectiveness. So that's all for me for the lateral stability. Thank you very much.
Hi, my name is Nurul Afifah binti Zulkifli. I would like to present to you about flight tests. Before doing the flight test, there are a few aspects need to be considered. First is event and activities. First, we need to understand the nature. Then done the calibration of the electronics part and the sensor, check the control surface of RC plane, set the location for pilot to stand, record the meteorological condition, in other words, weather condition, for example, temperature increase. Record data of RC plane and pilot, also record the flight path and flight time of RC plane. Second aspect to be considered is nature and environment. The flight test will be take place at UTM rugby field. There are few obstacles that are likely to face, which are rugby goalposts, trees, and net. Crowd will be around 50 people. Note that this is assumption we made before COVID-19. Since we are in EMCO phase, there are some rules to follow, SOPs set by the Health Ministry. So the crowd may change depending on the situation. The average ambient temperature in UTM rugby field is 32 degrees Celsius with the 1 ATM and 3.08 meter per second or 11.1 km per hour of wind speed. The third aspect to be considered is location of the pilot. The pilot should stand 3 meters away from the RC plane on ground before takeoff, and RC plane should not fly more than 92 meters from pilot since the frequency is 2.4 GHz. Last but not least, list of the maneuverability control when the strategy suddenly cut off. Glide angle of our plane is 1.25 degree with a stall speed of 9.52 meter per second. The movement of control surface is adjustable, so the aileron, rudder, elevator can be controlled manually by the pilot. That's all from me. Thank you.